All right, so you've probably seen this. This triangle is pretty famous. You see it when you deal with like graphics programming, typically around 3D. You're trying to draw something to the screen. If you're working on your own graphics library or game engine or something like that, the first thing you do is you say, can I get a triangle to the screen? There's a lot of work that goes into it. We're not going to make that today, but we're going to make something close. We're going to make this. We're not doing 3D, we're doing 2D, and we are going to generate this image that you see above, which is a nice little gradient. How are we going to generate that? We are going to use Bash. And when I say Bash, I mean pure Bash, okay? What do I mean by pure Bash? I mean we are not going to fork and exec any external utilities. So if you think this video is just going to be me running one little image magic command, no, that's not what's going to happen here. We are going to use Bash without using any sort of external utilities, any sort of POSIX utilities, GNU userland stuff, any sort of external commands, web services, anything like that. We are going to use Bash, and we are going to output binary data, and we are going to create a bitmap image. So yeah, buckle up. It's going to be wild. All right, so we got our terminal here. Let's go ahead and make a new directory where we can do our work. We'll call it bash BMP. And then in here, we have a completely empty directory. We'll make a script where when we run it, we will generate a BMP file. Okay, so right off the bat, let's talk about this first and get this out of the way. Bash is not great at dealing with binary data, but it can. Now let me explain what I mean by that. Reading binary data from Bash is not great, but writing binary data, it can totally do it. You know when you were like learning a language in school and you're like, oh, I can kind of understand it, but I can't really speak it? Bash is the opposite with binary. Bash can speak it, but I can't really understand it. Let me show you what I mean. If we have printf hello world here, and we run this, you can see it as hello world with a new line between it, no new line at the end. Cool. What if we wanted to save that in a variable? There's a couple ways to do this. Let's use this syntax. We can do this, and now our variable A will have all of that. We'll have a new line at the end because echo put a new line at the end of that string. Hey, cool. That's awesome, right? What if instead of a new line, we wanted to omit a null byte here? Let's go ahead and have printf print that. Well, it prints to the screen. There is a null byte there. We could verify. We could do cat -v. You can see it shows up there. We could pipe it to bat may show it. No, it considers it binary data. How fun. XXD will definitely show the null byte. You can see this 00 right between hello and world, and it puts it as a period here. That's great. What if we try to store that in a variable? What's going to happen? It's going to work, but we're going to get a warning. Ignored null byte in input. So then if we go to echo it, we have it right here. You can see that we get this here, but what about when we pipe it to XXD? You can see it's gone. It's gone. That null byte was removed. So at least we get a warning now, but Bash is really bad at reading binary data. But as you can see, it can omit binary data. So that might be all we need. So let's jump into it. To get started, let's make our little script here. We'll call it bash BMP, no big deal. User bin env bash, just your basic way of starting a bash script. Go down here and we can start doing something to do omit a BMP file. That's how we're going to handle this. So like I said, we're not going to be able to read in binary data. We don't need to read in binary data. We just have to be able to write it out and save it into a file. And as long as it looks like a BMP file, it is a BMP file. That's how computers work. As long as the file looks like how you want it to look like, it is that thing. It's beautiful. So if we run the script, nothing should happen because there's nothing in that script. That's awesome. This is the simplest bash script. It does nothing and it returns success. Hey, how awesome is that? All right, so I got the browser pulled up here and oh my God, what's this? Are we at my Patreon? How crazy is that? I have a Patreon account. If you like these videos, you can go ahead and support me, blah, blah, blah. That's it. No more sponsored content. Let's go ahead and close out of that and I won't pull that again on you. Let's start with the structure of a BMP file. So here we go. This is a bitmap file. This is what the binary file looks like. If this is scaring you, I'm so sorry, but don't worry. I'm going to demystify this whole thing and we're going to implement this. This actually means something to me and I'm going to show you how to read through this. I found this online. I really like this website because this is a very easy table to read and understand. So we're going to omit a file that looks like this using nothing but bash. So we're going to use this as our reference. So the first thing we need, if we want a BMP file, we need a 14-byte header followed by another 40 bytes of an info header. So multiple headers in here. And then our data comes below it. So what's the first thing we have to do? In our 14-byte header, we need to omit the signature, the file size, all zeros for 4 bytes because that's reserved, and then the data offset, that is where the data actually starts. So we're gonna have to actually calculate some things to make these header. Let's go back to the terminal and see what we got. Let's start copying over things from the table over to here because it's gonna be difficult to go back and forth. So I'm just gonna copy them over as comments. So we have the header, and then in that header, we have the signature, the file size, the reserved, these are all zeros, and then the data offset. So these are just copied from that chart, and this will be our header, which is, let's put this up here, 14 bytes. Cool. So the signature, if we go back to our data over here, take a look at this. It is just the characters BM. That's it, just the first two letters of BMP, and then we need the file size, then we need all zeros, then we need the offset. But the first thing we need is BM, so how do we do that? Super easy. Printf BM. There we go. Look at that. We're already writing a BMP file. How awesome is that? What's the problem with this? This is going to go to standard out. So when this script runs, we're going to output it to standard out. So we would have to execute it like this, out.bmp. We'll do that. We may change in the future, but for now, we're going to do this, and we're going to generate our BMP that way. So then if we run this, you can see that it doesn't quite look like a BMP. We're not there. The signature isn't fully done. So let's go ahead and keep implementing it. The next thing we need is to write a 4-byte file size. We don't know what the file size is going to be. The next thing we need is all zeros. We can do that, but how do we omit that? I'm going to get to that in a second. And then we need the data offset. So in order to get this information, we have to actually start doing some work here. And that's why I hate this, because in order to make the signature, the first thing, we need to know the entire size of the file, meaning we have to calculate everything we haven't done yet. So we got to do things a little bit out of order. So let's make some decisions. What should we do here? Let's figure out what size we want that image to be. So I did something, I think that triangle image was like 300 by 300 pixels. We can just pick an arbitrary width and height. For now, I'm going to keep things very simple. We will do a width of 2 and a height of 2. 2 pixels by 2 pixels. Very simple, very fast. We can iterate on this quickly, and we can start seeing some actual progress pretty quickly, which is nice. So in order to do this, we got to start calculating some information. If we go to the table, we can see what kind of information we have to calculate. So what's the first thing we need? The first thing we need is the size. So this is kind of weird. The info header is 40 bytes. We just need to put the number 40 here to say that the size of this block is 40. Then we need to put the width. Then we need to put the height. Then we need to put the number of planes, which as far as I can tell, I did some research on this. It's always just set to 1. Maybe this was some feature that was used before. I don't know. I couldn't find some. It seems like there's some history on this, but I didn't dig too far into it. We just need to set this to 1. Then we need the bit count. This is where we say what colors we're going to be using. We're going to go straight up 24-bit RGB. You can see right here. This will give us 16 million colors. That's because a 24-bit integer can store up to 16 million. So 8 bits for red, 8 bits for green, 8 bits for blue. This is your standard hexadecimal notation for colors. Compression, we're not going to use any compressions. We're just going to set it to 0. The image size, well, if compression is 0, we can set this to 0. So we're just going to omit some zeros here. So there's a lot here. I'm not going to go through the whole thing, but I am going to copy over some of the important stuff. So let me do that real quick. Go down here. Info header is 40 bytes. And let's start putting in the data for the info header. I'll probably just edit this because this will be kind of boring. Okay, so we're done. What I did here is I added the section for the info up here, and then I put all these comments here. So we're going to go ahead and fill this data in. This gives us a good little like skeleton. This gives us a nice little layout that we can fill this in. If we fill in everything here, we're done. So this is a really easy way to program. I like programming in this way. We have the width and we have the height. That's great. These are stored in variables. So what else can we do? Well, we need to know the bits per pixel. So if I show you, where is it, the website over here, we can see that we need the bit count here, and this is how many bits we're going to store per pixel. So in this example, it's going to be 24. Each pixel will have 24 bits because we're using 24-bit RGB, you can see right here. So we're going to store that in a variable, and then we're going to store the number of bytes because that's what the file size will be generated by. A little bit confusing. Hopefully I can talk you through it. So bits per pixel is 24. There will be 24 bits per pixel. Bytes per pixel is equal to, we can calculate this. That's bits per pixel divided by 8 bits in a byte. So this will be 3. I'm just telling you this will resolve to the number 3. That's because for each pixel, we will require 3 bytes to store that data. This is very important because we need to use this to calculate the file size. So now let's talk about the way colors are stored in a BMP image. If we go over here, we can see we have a color table here. We have 1 byte for red, 1 byte for green, and 1 byte for blue. And then there's this reserve section, which is going to be when we have to include padding. So it's going to be a little bit confusing, but bear with me. What we have to do is we have to calculate, we emit a full row, and then we move down and we emit the next row. Actually, that's incorrect. We emit the bottom row and then we move up. The way a BMP is generated, we actually draw the image from the bottom up, but we have to store it from the beginning of the file down. It's gonna be a little bit confusing. We might be a little bit inverted in the y-axis. I'll explain that as we go along. Basically, we have to store all the data horizontally and then move on to the next row vertically. So we have to figure out each row, how big is each row? We need the row size. So in order to calculate the row size, we can simply do the width of the image, which in our case is 2, and we can multiply that by the bytes per pixel. So if we have a 2 pixel width image and it takes 3 bytes per pixel, we need 6 bytes to store an entire row. Here's the kicker though. BMPs need to be aligned. They need to be aligned to a 4 byte boundary. What this means is each row needs to be a multiple of 4. If we don't have enough data to make it a multiple of 4, we have to pad it with zeros. So in my example, we have the width of 2 and the bytes of 3, that gives us a row size of 6. 6 is not a multiple of 4. We need to pad it with 2 to make it 8, so it's a multiple of 4. So it cleanly divides into 4 without a remainder. How can we express this in code? There's a couple ways. This is going to be the most complex math of the video, so hopefully this won't make you turn away, but it's not that bad. I promise it's not that bad. We're going to say while the row size modularly divided by 4, this is remainder division, is not equal to 0, then we do something. I'll explain what we do here, but basically, if the row size is not a multiple of 4, then we need to pad it. So let's go ahead here and let's say the padding currently is 0. If it's not a multiple of 4, then we'll do padding plus plus. So while the row size is not divisible by 4, we need to increment the padding and we need to increment the row size with it to keep these two things in line with each other. You could technically take the new row size, the old row size, divide, and blah, 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 blah. There's a couple different ways we could do this cleaner, but this I figure is the simplest math to sort of follow along with. We have a 0 padding by default. If it's not divisible by 4, then we up the amount of padding, we up the row size, and eventually it will become divisible by 4. And at the end of it, we will know how much we need to pad it by. So that's how we deal with that. Okay, now in order to calculate the file size, we need to know how much the data is going to take up. Now the data is each row. We already know the size of a row with all the padding, multiplied by the height, because that's how many of those rows will appear. Once we have that information, we know how big all of the pixel data will be. So we can go ahead and store that. Pixel data size is equal to the row size, which we just calculated, multiplied by the height of the image. So if there's 15 rows, we just take the size of each row and multiply it by 15, and there we go. In this example, it's going to be 2, but you get the idea. Now we need some other variables. So what we can do here is we know the offset of the pixel data. The pixel data will start after the 14-byte header and after the 40-byte header. So let's go ahead and keep that around because this will be useful. We'll call it, we'll just call it offset. Offset is equal to, what did I say, 14 plus 40, I think it was. Cool. So this is the size of both headers. That's where the pixel data starts. Pixel. No, you know what? We're doing this as we go along. There we go. Pixel data size, pixel data offset. There we go. Group these two together. It makes sense to logically put them like this. And then what is the last thing we need? We need to know the size of the entire file. So the size of the entire file size is really simple. We already know the size of the header. We already know the pixel data. So we can do pixel data size plus pixel data offset. And there we go. That's the size of the entire file. Bam, there we go. We have all the information we need. Now we just have to output in the right way, and then a computer can make graphics for us. How amazing is that? Took a while to get here, but I think we're gonna have something cool. Okay, so we printed BM. Now we need to print the file size. If you remember from the chart that I had here, I'll pull it up again. We can see that the file size is a 4-byte number, and it's the number in bytes that is the size of the file. Cool, very self-explanatory. So we can just echo file size, right? Not quite. Because even though we're storing a number here, when it gets echoed to the screen, it will be ASCII. We will get the ASCII representation of the number. That is not what we want. We want the raw binary number. Not only do we want the number, we want it to be put into 4 bytes, and we want it stored in little endian. I'm so sorry if you've never had to deal with little endian or big endian before, because I don't know if I can explain it all in this video, but I'm going to try and do my best, okay? We need to format the number we have in such a way where we can output it in binary in a way that makes sense in a BMP file. So let's go ahead and pull this up. I promise this will be the most technical we get, but it's pretty straightforward. If we have a number like this, in this example, we're using a 32-bit number. 32-bit numbers have 32 bits. We can break them into 4 sections of 8 bits. If we look at the number in hex, it makes it really easy to understand, because with hex, it's just sections of 2. So 1, 2, that's 8 bits. 3, 4, that's 8 bits. 5, 6, that's 1 byte, 8 bits. 7, 8, that's 1 byte and 8 bits. So when it comes time to store it, we can store it in this format, 1, 2, 3, 4, 5, 6, 7, 8, just like this. 1, 2, 3, 4, 5, 6, 7, 8. That's called big endian. That makes perfect sense to people that read from left to right. Unfortunately, we got stored in little endian, so we have to swap all of the bytes. We reverse the bytes. So when you look at this in memory, we see 7, 8, 5, 6, 3, 4, 1, 2. Very confusing for humans, very easy for computers, okay? So we're going to do this process in bash. So let's jump into it. So instead of calling echo here, we're going to call our own function. What function are we going to call? Well, I could name it something cute like make number or something like that, but I'm going to name it something very easy to understand if you've dealt with this stuff in the past, because we're going to print an unsigned integer that is size 32 that is little endian. Other languages have functions like this. You'll probably see something similar to this. You'll see all variants of stuff like this. You might see S16BE, assigned integer, 16 bits, big endian. That's all that means. So we are going to have a function called u32le. It takes a number and it will output the binary representation of that number. So we got to go implement that. Let's do that up here. u32le. There we go. And this will create an unsigned 32-bit little endian formatted binary number for us. Cool. Awesome. How do we do that? Well, first thing we can do is we can take the number, right? Because we're passing it as an argument. The number is $1. Very simple. The next thing we need to do is somehow convert it into a binary representation. How are we going to do that? How on earth do we do something like this? Well, printf. I'm still in Vim. Printf. I thought I was in navigation mode. Okay, so printf in bash can do this using a format specifier of %b. When you give it %b, it will interpret these literal backslashes. This is specific to bash. If I do a help printf, you can see that %b is right here. Expand / escape sequences in the corresponding argument. So we can go here, we can do printf %b, and then we can give it a string that looks like this. So /x for hex. Now we give it a hex number. The number could be anything. We could give it the hex number 0. This is a null byte. We go ahead and we print that. We could give it the hex number 1, and we can give it the hex number ff, just random numbers. And if we run this, you get really weird unprintable characters. If we pipe this to xxd, we can see that, hey, look at this. We have 00, 01, and ff. 00, 01, and ff. So, hey, that's how we turn things into binary. So what we need to do is we need to take that number that we have, convert it into a string that looks like this, and then run that string through printf. So we're going to be using multiple printfs here, but that's okay because printf is internal to bash. Printf is built into bash, is not an external command. We are free to use it, which is super nice. So the question becomes, how do we do this? We have a number, let's say n equals 5. How do we convert this into something that printf can understand? Well, the first thing we can do, and you need to understand this about printf, is we can give it %d, and I'm going to put a new line just so we can read it better. This is a format specifier. So %d will say whatever argument is given here, I will format it as a number, a decimal number. So when you run it, we get 5. Hey, that makes sense. There are some other cool things we can do with printf. We can say instead of %d, we could say %02d. This will pad the number up to length 2. So if it's smaller than length 2, it will be brought up to length 2, and it will pad it with this character right here, which is 0. So it'll put zeros to the left of it to pad it to that size. Super convenient, super nice. We have it set to 2, we could set it to 6, and then it would pad it up to 6. So we have this. What can we do now? Let's change the D to an X. Now we're going to format that number as hex. And there we go. Really boring because 5 in decimal is also 5 in hex, so that doesn't really help us, does it? Let's change it to something like 45. Let's rerun this, and we can see that we get 2D. How awesome is that? But again, this is not raw binary. This is just an ASCII representation. If we pipe this to XXD, we're going to get something completely different. Yeah, we're going to get 32, 64. These are ASCII letters 2D. And then we get 0A. This is the new line at the end of it that we put here. So what do we do here? We can store this information. Why do we want to store this information? Because we have the number we need. We need 2D. We just need those slashes in front of it. So we can store that in a variable. We could say -v, I don't know, let's call it out. And now we have a variable where if we look at the variable, it just has 2D in it. That's super cool. So we are very, very close. We can store that in a variable. What if we put a /x in front of that? What's going to happen now when we put this in a variable? It's good. Well, it's going to yell at us because it's going to try and interpret the /x. So what we can do, bear with me, I'm so sorry about this. We can escape the slash. There we go. So now if we echo out, we have this \x 2D as a string. So now we have our first printf, which creates that string. Now we can make our second printf, which will take that string and run it through the %b. So we need multiple printf here's, like I said we would. We can do this, and this will give us the raw binary version of that. We can prove it with XXD, so we can see that we get 2D. We get 2D. That is what we wanted in raw binary. So we have to go put this in our function, right? Oh, look at that WQ. Yeah, I'm really good. I promise I'm a good programmer. All right, so let's go down here, and what can we do? We need to take our number, our 32-bit number. We need to break it into all 4 sections. There are 4 octets in that number, and then we need to turn it into binary. So let's start putting some comments down. Convert number into 4 octets. Let's do an example here. Example, if the input is, let's do hex here because it's easy to understand. 1, 2, 3, 4, 5, 6, 7, 8. Just like that diagram online. Then the output would be octet 1 would be, what would be the first octet of this? 12. I have to make sure I get the ordering right because we're going to do little endian and big endian. I don't want to mess that up. Messing this up is a rite of passage as a programmer, so I'd actually be kind of proud if I pulled it off. It's similar to an off by 1 error. It happens. So 45, nope, that's not right. 56. And 78. So we're going to take this number, which is an actual number, and we're going to break it into 4 variables where this one is the number all the way to the left, which is the 12. This is the 34 section of it. As you can see, I could put the semicolons there. It might be harder, or the underscores might be harder to read. So let's go ahead and figure out how to do that. So we can do local octet 1 equals something, right? We have to do something. I'm going to use this notation, which means arithmetic expression, because we're going to do something with the number. So we have this number, we have n, and we need to get the 12 out of n. How do we do that? Well, here's what we know about it. This number is 32 bits, meaning 12 is only 8 bits of a 32-bit number, meaning 12 is shifted 24 bits to the left. So let's go ahead and shift it 24 bits to the right, because that's how we can get that number. So we could take n here, we could shift it 24 bits to the right, and then we'll be left with 12. The last thing we need to do, we don't need to do it here, but we're going to need to do it in the other number, so I'm going to do it because it's good practice. We need to turn off all the bits except the bits that we care about. So we logically AND it with the number FF, and that basically says turn off all the bits to the left of this. We only want the last, what was it, 8 bits. We only want the last 1 byte of this. So that's how we're accomplishing this. A little bit confusing, but hopefully it'll make sense when I start doing this. Let's take octet 2, octet 3, and octet 4. This we shifted over by 24. Nope, this becomes 16. This becomes 8, and this becomes 0. We could omit the shift by 0, but I think it kind of makes sense to leave it here. So we do this, and there we go. We have our number broken into 4 different numbers. So we have the first octet here. So if this was the input 1, 2, 3, 4, 5, 6, 7, 8, then we will have this here, we'll have this here, we'll have this here, and we'll have this here. In fact, let's go ahead and prove it because it might be useful to actually visualize what's going on. Input is n, echo octet 1 equals octet 1, and we'll just go ahead and, duplicate that. There we go. So let's go down here and let's do U32LE and let's give it some number. Let's give it like the number 45 here, and then let's just throw an exit here. This way we can run this script and just test our function. So if we run this, we can see that our input was 45, octet 1 was 0, octet 2 was 0, octet 3 was 0, and octet 4 was 45. I just realized I spelled octet wrong, but you know what? We're going to deal with it because we're this far into it. So 45 is a great number, but it's less than the boundary. So let's go ahead and make this bigger. What if we made it 500? Well, hey, look at that. We have 244 here and we have 1 here. That is correct. That's what we expect to see because there is 1 256 in the number and there is 1 244 in the number. When you add those together, you get 500. That's how that works. We can test it with other numbers, but it's going to be kind of pointless. I think 16 million is how many this can represent. No, that's not right. 65,535. Let's do, there we go, 65,534. That's a 32-bit integer. So you can see that we have 254 here, 255 here. We have 0 and 0. Oh, that's a 16-bit integer. Wow, I am all messed up. That is the max 16-bit integer, so it made sense that there were 0 and 0 here. I would need what a 32-bit integer can hold, which is somewhere around 4 billion if it's unsigned. So let's go ahead and do this. 4 0 0 0 0 0 0 0 0 0 4 billion. There we go. So we have 238 up here, 107 here, 40 in here. That's awesome. This is susceptible. This will technically overflow if we go too big. So hopefully we're not going to go bigger than this because we're not testing for it. Let's get back to work here. So now that we have this, we need to take this data and we need to output it in its binary representation. So based on that printf I had before, we can save this in a variable called out. Let's go ahead and declare out as local so we don't scope creep this anywhere. And then we need to store that in the format that we wanted it, which was \\x %02x for every single number. \\x %02x. So we just need to do that 4 times because it's a 32-bit integer. So there we go. We have that. And now we just need to format each number that we want. So we do octet 1, put a little \\, here. There we go. Don't forget to get rid of that one. We don't need that slash there. 2, 3, 4. And this will work, right? Because we put octet 1 first, and that's where the 12 comes from. Not quite. We're putting it first. That means we're encoding it as big endian. So right now this will work if we had big endian. We don't want big endian. We want little endian. We want to reverse this sort. So this is how you would make a big endian function. We don't want that. So let's do sort -r. There we go. Now it's backwards. Make sure to get the backslashes right. And there we go. Now it is properly encoded as little endian. Now we have a string that we can finally run through printf with %b. We just put the output string here and we're done. We are done. We are done. Oh boy. How can we prove this? Before I finish this, I'd actually like to prove this. So let's go ahead and put a number here. And here's a really, really cool trick with bash. We can actually give it hex numbers. We just have to tell bash that the number is hex. So it's not, we don't use 0x. We have to say 16 $, and that says that we are in base 16 here. So now we are free to put hex numbers here. So in our example up here, we use 1, 2, 3, 4, 5, 6, 7, 8. Let's go ahead and do that. 1, 2, 3, 4, 5, 6, 7, 8. So if we run this with that number, it should output it in binary, and we can test that by piping the whole thing to XXD. So we get 7, 8, 5, 6, 3, 4, 1, 2. That's right. That is what we wanted. That is correct. We took that number 1, 2, 3, 4, 5, 6, and then we formatted it as little endian. So you can see that's kind of backwards looking, but not quite. 7, 8 goes up, 5, 6 goes up, 3, 4 goes up, 1, 2 goes up. There we go. That is how we write 32-bit little endian numbers to standard out in bash. Now we have this amazing function. We can use this and we can start making some forward progress. So let's do that. Let's start making some progress here. So here we go. Look at this. We have the U32LE. We put the file size there, and that's right. We're done. Reserved. This was a 4-byte number, and it's all zeros. So let's go ahead and just put 0 there. Hey, that's awesome. Simple enough. The data offset. This is the file offset to where the raster data actually is. This is where the pixel data starts. Luckily, we stored that as pixel data offset. So let's go ahead and put that here. 32LE pixel data offset. See, this is the benefit of doing all that work ahead of time. Now we have these helper functions where we can just put them here and they're just going to write raw binary. How beautiful. Now we need, what do we need here? In the info header, we need the size. I'm going to go ahead and pull this back up just so we can remember what's going on here. I probably should have copied this over, but you know, here we are. So in the info header, the size is 4 bytes and it's set to 40 manually. Then we need the width and then we need the height. So let's go ahead and do that. We have the size that is set to 40 manually. We're done. Now we need the width, U32LE, height. Nope, that's not right. The width and the height. There we go. Then we need the planes. This is a number that is always set to 1, but here's the thing. It is a 2-byte number, and we don't have a 2-byte function. We're going to have to make one because what we want here is U16LE, and this will just be 1 because the number is hard-coded to 1. So let's go ahead and implement U16LE. Here's the great thing. We already did the hard work here. We already did the hard work with U32LE for a 32-bit unsigned integer little endian. Let's go ahead and do this, but let's convert it into 2 octets. And the way it'll look is it'll be that. And then we can get, this will be 8, this will be 0. Get rid of those. I didn't put 0, I put 9. Let's not go forward with that because that'll be a weird bug. And then we don't need that many of them. And we don't need 4 and 3. And we're done. That's as simple as that. We read in a number. Simple as that. Let's go ahead and change this. We read in a number. We get the first octet. We get the second octet. And then we format it in reverse order because it's little endian. And then we turn it into binary. And there we go. Now we have a U16LE function we can safely use. Hey, that's awesome. Let's go back to our table and see what else we need. We got a 2-byte bit count. Here's the thing. These bytes actually mean something. So as you can see, if we put the number 24 here, we get 24-bit RGB. We already stored that above, which is pretty cool. We stored that as, I think it was bits per px. Bits per px. That's it. Bits per pixel. So let's go ahead and use that here. Is it 16 or 32? It's 16. U16 bits per px. Compression. Let's go ahead and pull this back up. Compression, we can set that to 0. We're not going to use any compression. And the nice thing about that is if we don't use compression, we can set the image size to 0. We don't need it. And then here are some other things here. I'm not going to dive into them because they're pretty much just going to be unused. We are just going to set these all to 0. Horizontal resolution, this is stuff for when you go and print the file. We don't need that. We can just set it to 0. Number of colors actually used, number of colors that are important. We're just going to say that we're using them all. And we're not using any sort of palette. We're using true bit 24-bit coloring. So we just set all this to 0. So basically, we are going to write 4 bytes. We're going to set it to 0 6 times. So let's go ahead and do that. The compression, U32LE, 0. Easy. Image size, 0. Pixels per M, 0. Y pixels per M, 0. Colors used, 0. Colors important, 0. There we go. We have the header of a BMP file done. How beautiful is that? So let's go down here, and now we have to just start writing our color data. So we have to emit RGB values. Remember, we're doing 2 by 2, so we need to just emit a random color 2 times, and then we need to pad it, and then we need to do 2 times, then we need to pad it, and we're done. Like, that's it. It should just work, right? So how are we going to do this? Let's figure it out. Okay, so like encoding a number here, we can encode 16 bits and we can encode 32 bits. We need one that's in the middle. We need one that can encode a 24-bit number because that's going to be the R, the G, and the B. So as long as we can encode a 24-bit number, we're good to go. We're not going to call this U24LE, and the reason for that is because we're actually going to make this function a little bit smarter. We're going to copy it because it's pretty much the same, but we're going to make it a little bit smarter. We are just going to call it RGB, and we're going to give it 3 values: R, G, and B. So these will be the colors. The person can call this function with 3 different colors, a number between 0 and 255, and then we will output that color pixel data. And the way we can do that is it's super easy because we have R, G, and B. We can just do what was it, local out, I think is what we called it. We just need this. We don't have to do any formatting of the data. It's already been given to us. We're going to bring this down to 3 of them. As you can see, we're going to format 3 numbers, and those numbers are R, G, and B. That's it. That's as simple as that. Hold on though. Here's something fun about BMPs. Are you ready for this file format? They don't use RGB. They use BGR. So similar to how like Little Endian has it backwards, this one's backwards as well. So we have to do BGR. Our function will take RGB, but when we actually emit the data, it will be BGR. So what do we do now? We are so close to being done. Let's hard code this just so we can work with something. We know that we have a width of 2 and a height of 2. So let's do an RGB of, let's say, all black. We'll do an RGB of all white. So that'll be 255, 255, 255. Now we need to pad it a little bit. And how are we going to do this? Well, we know what our padding is. I think we stored it. Yeah, we just stored our padding as padding. So let's do this. For I equals 0, I less than padding, I plus plus. We'll clean this up later. Don't worry about it. Printf a null byte. This will print just a literal null byte, which is just a bunch of zeros to the screen, which is what we want. This is what the padding is. So we'll print 2 pixels. We'll pad it. We'll print 2 more pixels, and then we'll pad it. So we could change these to be other colors. We could do, I don't know, let's do red here. So that's R being set to 255, G and B being set to 0. And then let's do, I don't know, green here, 255, 0. So this should be it. Moment of truth here. We'll see if it actually works. We'll see how good of a programmer I actually am. If we take this and we write it out to out.bmp, seems like it worked. We have a success error code. Let's go ahead and open out.bmp and see what we get. So close. The file out.bmp could not be opened. So we did something wrong here. Let's go ahead and debug this because this will be fun. Let's figure out what exactly we didn't do right. You see it? I see it. You see it? Look at my cursor. Bits pre-pixel. Let's open it. Moment of truth. Something opened. It looks like there's some data here. Let's go ahead and zoom in on that. Remember, it's a 2 pixel by 2 pixel. Hey, look at this. We have black. We have yellow. We have a little bit kind of black and zeros. So, kind of. We got something. We got a 2 by 2 image. The colors don't look quite right. What colors did we use here? Let's go ahead. I'll close this out. Let's go ahead and look at our colors down here. So what we wanted is we wanted black next to white and we wanted red next to green. We didn't quite get that, so something is a little bit wrong here. Look at this. Another typo. If you're watching this video, you're probably yelling at me. Go ahead and yell at me in the comments right now because I'm stupid. What is BGG? BGR. That's it. So let's rerun that, reopen that, zoom in. That's annoying. That sound needs to change. Let's turn that volume right off. This looks great. Now, like I said before, remember, BMPs go from bottom up. So that black and white pixel is at the bottom of the image. And then we have red and green here. We've created an image. With Bash, we have created an image. How impressive is that? So what do we do now? Let's clean this up because the code is a lot. The code is very much a lot to work with. We can clean this up by starting to put things in functions. So we have U32LE, we have U16LE, we have RGB. Let's go ahead and make a function called BMP header. Okay. This will be a function that takes a width and a height and then emits the header data to standard out. That's what's going to happen here. So we have our width equal to 2, our height equal to 2. Let's go ahead and delete those and grab everything here. Everything except where we actually emit the color data. Delete it, bring it up, put it in the function. There we go. Let's change that indenting, and now everything is in a function. Because everything's in a function, we should be good. Let's start declaring these local so we don't scope creep. We don't lose track of any variables. There we go. There we go. Beautiful, beautiful, beautiful. So we have our BMP header function right now. That's really good. So we should be able to do something like this. Width equals 2, height equals 2, BMP header, width, height, right? There's one little problem here. Look at this variable right here, padding. We don't have access to padding. Padding is declared in this function but we don't return it. Here's the thing about bash. We can't really return values from a function. We can only emit things to standard out. And this is already emitting raw binary data to standard out. So that channel's used up. What we can do though, is we can use a variable that bash uses. This is sort of a convention. A lot of bash built-ins use this, called all caps reply. So we need to get the padding out of here. So what we can do at the very end here, we can say reply equals padding. Notice how it turned purple. This is a special variable to bash. Special in that it's just convention, not special as in like there's some sort of magic around it. So when this function's done, we can just do this. Padding equals reply. And that was our way of getting out of it. Reply is just a global variable that we can access. So now that we do this, this should still work. So let's go ahead and test this just to make sure we're not crazy. Out.bmp. Looks good. Let's go ahead and open it. And hey, we get an image. If I zoom in, hey, that image looks right. So that's working. That's good. We've moved that into a function. Let's keep going. Let's make a main method here. Move everything into the main method, and then we can just call main with the arguments here. We're not taking any arguments, but this is just good practice. And then this is our function to make an image. We have our width, our height, we get our padding out of it. That's great. And then we emit color data. We do have this logic duplicated for padding, so let's go ahead and put this in a helper function. So where we have BMP header, we could have BMP padding. And this will take the amount of padding that we want as an argument. So we can just do this, and this will just print null bytes for us. This way, what did I call it? BMP padding. I don't like that name. Let's call it BMP pad. There we go. This way we can just do this. BMP pad padding. BMP pad padding. There we go. This is a lot easier to read, a lot easier to understand. So if we rerun this, it should just work. I don't expect it to break because we just move things into functions. Hey, that looks pretty good. Awesome, cool. So we are cleaning this up nicely. So what do we have here? We have our U32LE, our U16LE, our RGB function, our BMP pad, and our BMP header. We're calling everything BMP. I kind of want to call this one BMP also. So then, yeah, this looks nicer to me. I'll leave the U32 and U16 the same because they're technically like internal functions. So hey, this is pretty easy to understand. Bottom row, top row, just so we can understand what's going on here. So now that we have this, I want to make some more files. So we have our bash BMP script, but we could have other scripts. We could have our gradient script or something. So let's go ahead and extract this out into a library that we can source. Make dir lib cp bash BMP into lib BMP. So I've made a new file, and you can see, oh, I don't have the tree command on here. Lame. I have a new file called lib.bmp. So if we ls lib, there it is. Let's go in there, and it's just going to be a library file. That is all I want. It's just going to define functions for us and nothing else. So we have our RGB, our pad, our header. That's awesome. So let's just get rid of the main method call. That's it. Just getting rid of the main method call. And the reason we're doing that is because these functions will do everything we need. Then if we go into our bash BMP, let's move this file actually. Move bash BMP to simple BMP. And simple BMP can pull in that library, exit if it fails, and then we can get rid of these functions, which is super nice. So we're cleaning this up like crazy. That's it. There we go. This should just work. Look how simple this is. So this script, if we run it, will just, I think it still outputs the standard out.bmp, open out.bmp. Again, we haven't changed anything. We've just moved everything into a function for us. Hey, that's super cool. That's super awesome. So our simple BMP just emits it to standard out. That's super great. What we could do here is we could take a file name as an argument and emit it there, blah, blah, blah. Let's not worry about that now. This is just the simplest version of the script. This emits a very simple BMP file to standard out. There we go. Might as well put the licensing in there. Hey, take a look at that. How beautiful is that? There's my license data. What was that unprintable character? I don't know what file just showed up there. There we go. MIT license. All this code, MIT license. So let's make a new one. We have simple BMP. Let's do the thing I said we were going to do. Let's make our gradient. So now we can make a new file here. And this function just has to make a gradient. Emit a gradient BMP image. Let's circle back to that in a second. So here we go. All right, so how are we going to make a gradient? Well, the nice thing is this is actually very simple because it's just a series of for loops. So we have our width of 2 and our height of 2. Let's go ahead and make those, I don't know, let's say 400. Arbitrary numbers, 400 by 400 pixel image. Hey, that's super simple. So let's go ahead and start defining some variables that we'll need. We'll need R, G, and B because we're going to set R, G, and B. And then we're going to create a for loop. We'll have to define more variables here. Not a big deal. We're going to loop over every possible row first, and then we're going to loop over every column in that row. So we're going to construct the image basically in real time here. So we're going to loop over the y-axis. We're going to loop over the x-axis, x less than width, x plus plus, do, done, done. And then we're going to need to do some sort of BMP RGP here. And did I say RGP? I meant RGB. Oh man, been at this for a while now. And then we just need to put our BMP pad here. So what's happening here? That might be a little bit confusing what just happened, but I'll explain it. We're looping over all the Y's. So we're going from top to bottom, or in this case, bottom to top. And then inside that, we're looping over every left to right. So for every left to right, for every single pixel, we need to draw a pixel of the screen. And then once we're done with that row, we need to put the padding there that needs to be there. And then we're done. It's as simple as that. So the colors are the important part here. We need to set R equal to something, G equal to something, and B equal to something. So let's do that. Let's say R equals, you ready for this? Let's take the x-axis, arbitrary. It could be either one, doesn't matter here, times the maximum it could be, the maximum color can be, which is 255, divided by the width of the image. Might be a little bit confusing, but basically where that X falls is going to be multiplied by the biggest color it could possibly be and divided by the width. So it will go from 0 to 255. All the way to the left of the image, it'll be 0. All the way to the right of the image, it'll be 255. So on the left of the image, there'll be no red. At the end of the image, it'll be full red. That's the idea here. We can do the same with green or blue. I'm going to pick blue, arbitrary here, and let's change this to Y, and let's change this to height. So Y will go basically from the bottom, it will have 0 blue, and at the top it'll be full blue. Or I might have that backwards. We're going to find out. That's the beauty of doing graphics programming. If you make a mistake, they look beautiful. Like truly, I mean that. It's a ton of fun. So what are we going to do? We're going to call BMP RGB with 3 values. The R value we calculated, a hard-coded 0 for green. There's going to be no green in this image. And then the B that we calculated. And guess what? We're done. We're done, right? Out.bmp. We run that. Who knows how long it's going to... That was actually way faster than I thought that'd be. Okay, I kind of expected that to take longer. I'm going to be real with you guys. Yeah, that was way faster than I expected. That's awesome. I had a whole plan to show how to add debug lines, and wow, this computer's fast. Let's open this up and let's see. That's it. That's it. That's what I promised we would make at the beginning of the video. Here it is. Look at it. It's beautiful. It is a 400 by 400 pixel image. As you can see, there is no red. Where is there? No red at the top, and there's full red at the bottom. There's no blue on the right, but there's full blue on the left. Like, this is cool. I may have described that wrong. This is really cool. We generated this with nothing but Bash. How awesome is that? Can we do more? Of course we can. Let's have a little fun here. We have our gradient script. I wanted to add some debugging, so I'm going to go ahead and do this anyways, because I was going to show something I think is really important. I'm going to make a debug function where we just print the word debug, and then we print whatever arguments were given to the debug function, excuse me. The reason why I wanted to show this is because if I were to call the debug here, like let's say debug handled row Y out of height, if I put this here, there's a problem. Because remember, this is omitting binary data to standard out. We can't also omit log lines. Those log lines will end up inside the BMP file, and then it'll be invalid. So we need to output these debug lines to standard error. Standard error is file descriptor 2. That way we'll see them on our terminal, but we'll also write the data into the BMP file. So there you go. Now you get an idea of how fast the script is actually running. That's what I was going to add before, but it just ended up working way faster than I expected. So that was super cool. So what can we do now? We have our nice little debug function. We can make some of this stuff configurable. So we have a main method here. Let's go ahead and make a function called make BMP, and make BMP will take a width. It'll take a width and it'll take a height, and then it will make the gradient for us. So let's go ahead and grab this stuff and let's move it here. So now we have this function make BMP. Why is that important? Because we can run make BMP and we could write that out to out.bmp here in our script. How cool is that? Because we can specify the width and the height. We should actually probably pass those in. And now we can make it configurable. So how do we do that? Well, we can use some getops here. While getops. In order to do that, we need a local opt-in, opt-arg, and opt. While getops will take a width, we'll take a height, and we'll take an output file name. How's that? So we can say opt do case opt in. This might be confusing if you've never seen this, but I'll show you. Hopefully this will demystify some things right here. If the user gave us W, then we will set width equal to whatever they gave us. If they don't give us a number, hey, tough luck. Our program's probably going to break. If they gave us this, which is a height, we can say height equals this. And if they gave us O, which is output, we can say output equals opt-arg. ESAC and done. AO. So now we can say local output equals, what we want the default output. Let's just say out.bmp. So if the user calls this without a file, we'll write it into their current directory called out.bmp. Otherwise, we will do this with whatever they gave us. We could overwrite a file if they give it to us. This is just something to keep in mind. But what does this mean? What does this mean? We can run gradient with a width of 200, a height of 200, and we can write that out to out.bmp. Open out.bmp, and there we go. Now we have an image that was half the size. We could do something like a width of 200 and a height of 600. And we can run this, and as you see, it has to crank through 600 now, but when we go ahead and open it, you can see that, hey, look at this. It's a portrait style. It's way taller than it is long. So that's pretty cool. We made those configurable. We can add some more stuff here. We can say echo generating image width by height. And because we have a little X there, we have to do this. Width by height. Let's put it here. Generated image out. There we go. So now we know where it was saved. And we can do an exit here. If that fails, that's our nice little error checking, and we're done. That's as simple as that. So let's go ahead and rerun this. We can do, let's just do a simple 200 by, 50. Run this, and then we can see generated 200 by 50 image, and then we printed the word out, which is bad because we called it output. If only I had remembered that. There we go. Open out.bmp. There we go. Hey, look at that. Beautiful. We generated the gradient. So, can we make something useful here? Like, we have a gradient. That's pretty cool. That's awesome. But, like, can we do something kind of useful here? Well, the answer, of course, is yes. So let's make some pixel art. Let's get started. Let's vim, what do we want to call it? Smile.text. We're going to make some pixel art right on the fly. I'm not great at this. It's not going to be beautiful. But here we go. We have periods, and then we're going to put any sort of random character here. Let's just use O. We'll put some O's up here for eyes. It's trying to do spell checking on this, so set no spell, turn that off. And where do we want the eyes? There we go. That looks good. And then we can do like a nice little like, there we go. It looks like a smile, right? Wow, I'm surprised I got that even. So there we go. We have two characters, a period and an O, and it looks like a nice little smiley. So if we were to highlight the O's, you can see that, hey, look at that. It's a nice little smiley thing there. That's beautiful. Now let's make an image based on that. So let's CP gradient, because we've already done a lot of work there, into, let's call this sprite to BMP. There we go. So now we have this where we read in some data, we read in the width, we read in the height, and we take an output file. We don't want that anymore. We don't want the width and the height to be taken from that. The width and the height will be written from the file. So let's go ahead and pass the file in as standard input. The output will still take as O, because that's kind of useful. And that's the only argument we'll take right now. We may change this in the future, but let's go ahead and just do this. Make BMP, and we'll write it to output, generated image, store it there. Beautiful, awesome. So now in our make BMP function, we have to get the width and we have to get the height. How do we do that? Well, we have to read the sprite data. How do we do that? We're going to read into a function or a variable called sprite. We can use map file. Map file -t sprite. Map file will read a file from standard in by default, and it will store it as an array. So we will now have an array called sprite that will have the input. So for example, you would call it like this, where you could cat it, or if you didn't want to use cat, you can do it this way. It doesn't really matter which way you do it. So we're going to read that file in, and we're going to do some work based on that file. So we need to get the height and the width out of it. Well, where is it? We have height and we do width and height. Okay, look at the width first. The width is easy to calculate because we just take the length of the sprite at array spot. It doesn't matter because all of them are the same. So we're going to get the length of the line, the first line of the file, and that's our width. And the height is the number of elements that are in there. So for the height, we just take the number of elements that are in the entire array. There we go. So now we have the width, now we have the height, and we can go ahead and just make our image. Oh, I totally just realized that I never actually made Y local and I never made X local. So let's go ahead and do that in our gradient function. X and Y, there we go, awesome. So let's go back to our sprite thing here. We have RGB, X, Y. We need to figure out what data to use in what location. So instead of hard coding these colors like this, well, I shouldn't say hard coding. Instead of calculating these colors like this, we can get the character in that array that we have. So we can grab the sprite. We have to get the row that we need. It is going to be inverted on the y-axis, so we're going to uninvert that here. We're going to take the height minus y minus 1. That's how we're going to grab the character. This will grab the row where the character is. Now we need to actually extract the specific spot of that. The way we do that is we take a substring of x, which again is the length over that it is, and we want one character from it. There we go. Now we have our character called C. In our smiley, our character is going to be a period or an O, so we can do a nice little case statement on this. Case C in. If it's a period, then we want, let's say R equals 0, G equals 0, B equals 0. And if it's an O, then we can say R 255, G 255, and B 255. And if it's anything else, we can just exit 1 because whoopsies, we don't expect that. So now that we have that, we just output the RGB value here. Let's go ahead and actually output G here. So hopefully this makes sense what we're doing. We're looping over the X and Y of that input smiley file. And we're looking, if we have a period, we're going to make it black. If we have an O, we're going to make it white. We're going to output that data. We're going to pad it. And is that it? Is that it? Let's go ahead and cat smile, pipe it to sprite to BMP. And it says it generated it. Let's go ahead and pull this file open here and look at this. It worked. It worked. How amazing is that? We can generate pixel art using Bash. How crazy is that? There's no limit to the number of characters here. We have O and we have what, period? We could have any number of characters be any color. We can have colors be calculated. We could pull colors out of a palette. There are so many options here. It's actually kind of nuts. Let's go ahead and add a palette to this. I think it'd be kind of fun to add a palette. So I pulled this up here. This is just a palette I found online. It's for the Nintendo Game Boy. As you can see, there are 4 different colors here. We have these different colors and they're all in hex, and then it nicely gives us their beautiful little RGB values. How fantastic is that? So we can just take these and use these colors. Let's go ahead and make our own file format for palettes. This way we can easily customize it without hard coding colors into our script. So let's say palette.text, and this will be just a basic text format where we can say the character that we want. So in this case, it would be a period and then a space, and then let's give it the color that we want it to be. So we're going to go ahead and grab these. You can't see this, but I'm just grabbing it from that website I showed you. And there we go. I changed the O to a 1, 2, and 3. So we have a period, a 1, a 2, and a 3. And then we have the hex value for the color that it should be. That's super great. Let's go ahead and add some logic to our sprite2 BMP file to actually load that palette in. So let's do this. Let's add P, and P will be palette, and palette will be opt.arg, local palette, and then if, let's say, -n palette, we'll enforce that the user must give us a palette. They have to give us a palette, otherwise we just exit. So now that we're down here, we know we have a palette file. We need to load palette, and we'll give it the file name that we want to load. So now we need to write a function that can take a file and that can actually load a palette from that file. All right, so I'll make the function here. And just like we loaded the sprite data with map file, we're going to do the exact same thing here. We're going to load the lines of the file using map file -t. We can put a variable here, so lines is the name of the variable, and then we'll read that in from the file, or we'll return 1 because something went wrong. Let's just actually exit here. This is very aggressive error handling, but this is meant to be educational, so here we go. We need a define file. We can't just call it without defining it. So let's go ahead and put that up here. We have file equals $1. We have lines down here. Now we need to loop over those lines. So for line in lines, do done. And now that we're doing this, we can parse each line. So remember, it was the character, space, and then the hex value. So we can do this. We can say local C and hex, C for character and hex for the hex string. We can grab the character by taking a substring starting at 0 for 1 character, and then we can take the hex portion of it by doing line starting at 2. So this will get rid of the character, this will get rid of the space. Now we'll just have a pound sign and the hex number. So we need to parse that. We need to parse a hex value in Bash. How do we do that? Well, we're going to need a hex2 RGB function. This will take a hex string and return it as a number, space, a number, space, a number, where the number will be 0 to 255. So let's go ahead and imagine what that would look like. This will take hex here. This should be defined as hex, and then we will store that somewhere. I haven't gotten to where we're going to store that yet, but we're going to store that somewhere. So let's go ahead and implement hex2 RGB. So the first thing we need to do is we need to store the hex string, and the user gives us it through $1. That's super useful. It's going to have the pound sign at the beginning, so we should trim that off. It may or may not have a pound sign, so let's use this notation. Starting from the left, look for the literal pound character and delete it. So if it was there, it will get deleted. If it wasn't there, no harm done. So we'll get rid of the pound sign that way. Now we just need to extract the R, the G, and the B. So what does that look like? Well, we had this notation, I mentioned it before. We can do 16 pound sign, which means interpret it as hex. And the number that we're going to take here is hex, substring at 0, go for 2 characters. And that's it. That's it. That's all we have to do. Now we just change this to 2, change this to 4, both for 2 characters. And there we go. Now we have our R, G, and B values as numbers in decimal notation from 0 to 255. Now we can just echo those as R, G, and B. So they're separated by spaces. So now we call that function, we get this. What do we do with that information? We're going to make a global variable up here called palette. There we go. This is an associative array where we will have a key and value pair. So right here, we can say palette equals, we can give it a key here. The palette at character C equals the hex2 RGB of that hex value. So now we have an associative array where we can give it a character and it will spit back a color that's suitable for that character. So where we have this case statement where we check characters here, instead of that, we can do this. We can say local R, G, and B. We can read in from the palette. So we're going to read the R, the G, and the B value from the palette at character C. There's not much error checking here. Things will default to just being 0. So we'll get black if we don't understand the sprite color, which is pretty cool, or the pixel color for the sprite. We can get rid of all this stuff here. That's it. All we're doing is we're basically saying, hey, look at the palette, find that character C. It's going to have an RGB value, extract it into variables called RGB. and then just run it. So if we did everything right, this should just work. So we should be able to cat smile into sprite to BMP, and then we can give it the palette of palette.text. This won't quite work. The reason it won't quite work is because I didn't change these O's. So let's go ahead and change those O's to just the number 1. We can just mess around that way. And then we should be able to run it and it should work. I think it's still gonna fail. No, it actually worked. Okay, ignore what I think. Apparently I don't know what I'm doing. Let's go ahead and load this up. We have pixel art with the palette. How perfect is that? Look at that. That's beautiful. Now we are free to do anything here. We're only using some of the palette. We could go ahead and make the eyes, I don't know, make them 2, and then we can make this one 3 if we wanted to. I have no idea why you'd want to do that. We can replace all these with 3s. Here, you know what? Actually, yeah, let's just do that. Put the top and the bottom as 3s. We have 2s for the eyes and 1 for the mouth. Let's go ahead and let's run that again. Let's open our out.bmp. And there we go. Look how beautiful that is. Wait, do we have the 3s at the bottom? That's why 3 wasn't showing up. I copied it wrong. Oh man, I should always check my work. This is why graphics programming is fun. I mean this. I actually mean this. When you make mistakes, they show up visually. How cool is that? That is such a cool way to see mistakes. You literally get to visualize them. I think that's such a cool thing. So if this works, we should have a top and a bottom to this image. Hey, we do. I'll make this a little bit bigger. You can see we have green at the top. We have green at the bottom. The mouth is slightly lighter and the eyes are barely visible. There we go. We have 2D sprite generation using nothing but Bash. So there we go. We could generate an image just completely in Bash. So I don't know why. I don't know why I did this, but it was a ton of fun. If you stuck around this long, thank you so much. I appreciate it. I hope you guys are enjoying these pure Bash videos. Go ahead and hit that like button, subscribe, comment, do all that fun stuff, dude. I super appreciate it. My last video where I talked about making a web server in pure Bash, if you're into this sort of thing, go check it out. I'll link it at the end of this video. I got such good reception on it. I was like, I gotta make more pure Bash videos because people seem to love it, and I have a ton of fun making it. So yeah, I think I'll stop there. We have a gradient one, we have a simple BMP, and we can turn sprites into bitmap images. How cool is that? That's super awesome. I will make all this code. It's open source. I will make it available on GitHub, so I'll have that link below by the time this video comes out. And yeah, I appreciate it. Thank you so much for tuning in, and yeah, take care, everyone. And like I said, I made a video where I talked about making a web server in Bash, so go check that out. I'll link that there. See ya.